Okay. So last time we were talking about the two kinds of elimination reactions that we have for amines. And they're both going to form the less stable product. So what we had done last time was, let's say we start with a primary amine. If I want to do Hofmann elimination, I first of all need to react that amine with 3 equivalents of a methyl halide. Methyl iodide is what's normally used, but it could be methyl bromide. And I have to do that under basic conditions. And if I remember, I'll tell you exactly how that's done. So the idea here is that I end up taking that nitrogen, adding 3 methyl groups to it, so that I end up with the ammonium salt. Now the basic conditions, remember, every time I alkylate an amine, you get an ammonium salt, and then you have to react that with base in order to convert the N plus back into a free amine that will be a nucleophile. So we alkylate that 3 times. We alkylate it 3 times. And then what I'm going to do is then I'm going to apply heat to this reaction. And as I'm applying my heat, I'm going to lose the H plus and the ammonium as ammonia. Okay, so the issue is, since this is the alpha carbon, here's a beta carbon with a hydrogen, and then there are 3 hydrogens on this beta carbon. And so the mechanism is such that the carbon with the most beta hydrogens is what's going to lose. So in other words, the conformation, whichever beta hydrogens, whichever beta carbon, I guess, can put hydrogens in the most number of conformations, is going to lead to the major product. And so all 3 of these can become anti-periplanar to the leaving group, whereas over here I only have 1 hydrogen. So the major product of this reaction is based on the number of beta hydrogens, with the most beta hydrogens being the major product, which means that I'm going to form the least substituted double bond. And so I'm going to lose this hydrogen, and then the nitrogen is going to leave, so that in my final product is going to look like that, plus most likely the ammonium will reform. So there's no base. This is totally based on heat. So this was Hofmann elimination. So that was the first one that we did. Then the second amine elimination also produces the least sterically hindered, or least substituted double bond. And so same molecule. I'm going to start with my amine, only this time I'm going to alkylate it twice. So I'm going to add 2 equivalents of a methyl halide, again under basic conditions, and now I'm going to add 2 methyl groups to the nitrogen to give me not an ammonium. There's no plus charge there. To give a tertiary amine. Then I'm going to react this with a mild oxidizing reagent, either hydrogen peroxide, or you can also use a peroxy acid, and that's going to convert the amine to an amine oxide. So I'm going to have the two CH3 groups, but now I'm going to have an O minus and then convert that nitrogen to an N plus. So this is the amine oxide. And I'm going to assume that the mechanism here is just going to be simply based on that O minus finding the least sterically hindered hydrogen, because that's kind of what would make sense here. So that again, with 3 beta hydrogens and only 1 beta hydrogen on this side, and that beta hydrogen being more sterically hindered, the O is going to go after the least sterically hindered of the hydrogens to give the least substituted alkene. This pair of electrons will come over and grab the hydrogen. A pair of electrons will move there, and then a pair of electrons to the N plus. So that I form that alkene. And I form what's called a hydroxylamine. And this is what's called Cope elimination. Sorry. Yes. Yes, because what I have to do in Hofmann elimination is what's called exhaustive methylation. So I have to put as many methyl groups on the nitrogen as possible. For Cope, I need 2 because the 4th position is going to be that single bond O minus. So that's going to be, that's how you can tell the difference. Obviously followed by the fact that I put 3 methyl groups in heat. I put peroxide, react with peroxide, and then apply the heat. So that's how we would tell the difference between the two. Both of them will form the least hindered, or the least substituted product. But they differ in the fact that this transition state has to be periplanar in terms of its relationship of the N, the O, and the H. They have to be in the same plane. And so it's not an E2 mechanism. Whereas if we go back to the Hofmann elimination is more of an E2 mechanism, and so it will undergo anti-periplanar transition state. Right, so that's the difference between the two. And we're going to add stereochemistry to this in a minute so that we can see how that would differ, how these two reactions would give two different products. Okay, so that's where we were at last time.
Is one better than the other? So what would make you like one over the other if they both give you the same product?
Well, they'll both give you the same major product, but they will give different stereoisomers. So here's the example that we're going to look at. So I'm going to put my NH2 molecule here. I'm going to have a hydrogen, and I'm going to have a methyl group. And then here I'm going to have a methyl group. I'm going to have the beta hydrogen, and then I'm going to have an ethyl group. So if I started with this molecule, I could do either Cope or Hofmann, and we're going to do both of them. We're going to see, not necessarily they'll both give the same major product, but it's the other product that's going to be slightly different. Okay, so that's what we need to look at. So how am I going to do that? Well, let's say I add my 3 methyl iodides, and at this point, let me show you what the book uses. The book uses silver oxide. So you'll see this with methyl iodide, silver oxide, and heat will be the reaction conditions. So the first thing is I'm going to alkylate it 3 times to form the ammonium. And then the heat is what's going to cause the elimination to occur. Then over here, I might use 2 equivalents of methyl iodide with silver oxide, and that's going to add 2 methyl groups to the nitrogen, so it's going to be just a tertiary amine. And then the left carbon, nothing changes with it. And I'm going to write ET for F. And then I'm going to apply heat to that. Now this methyl iodide silver oxide is how the book writes it, and it's traditional. And so let me explain what's going on with that. So what's happening with the silver oxide is this. You'd have to go back to general chemistry, but do you think silver oxide is soluble in water? What? Well, oxides in general, unless they're sodium, potassium, or cesium, or ammonium, tend not to be soluble. Oxides, sulfides, those are things that are generally not soluble in water. So I could write an equilibrium reaction where that breaks apart into silver and hydroxide. Particularly if I put water on this side, so that the oxide will react with water to form hydroxide. Now that's an equilibrium, so what happens is that when I add my first methyl group to the amine, it forms the ammonium salt. That ammonium salt will react with whatever hydroxide has dissolved in solution to neutralize it. And then the silver oxide just basically produces more hydroxide as necessary to neutralize any ammonium salt. So I don't have to keep adding hydroxide. The silver oxide, whatever is needed, will be produced as it's formed. And it's an expensive way of doing this, but it'll work. So that's where the basic reagent comes from, is from the silver oxide. So when you see that in the book, that's what it's doing, is it's taking the amine, after the amine's alkylated, it's taking the ammonium and it's neutralizing it to the free amine. Now, going back to this reaction, here's my alpha carbon, here's my alpha carbon, here's a beta carbon, here's a beta carbon, here's a beta carbon, and there's a beta carbon. So I'm going to label these hydrogens A, and I'm going to label this beta carbon B, or beta hydrogen B. So my question is, what beta hydrogen is going to be lost to form the major product? A or B? So if you have your card, you ready? So which hydrogen is gonna be lost to form the major product, A or B? Fourteen A's and 4 B's. A wins. And why is that? Because like I said last time and a few minutes ago, I'm going to form the least substituted double bond. So that's great. Major product is going to look like this. Is it? Yes. Oh, sorry. There's an ethyl group there. There's the major product. Now, what I want you to tell me is what the next major product is for each. Let's do Hofmann. Let's do Hofmann. So for Hofmann elimination, what is the second major product going to look like? Well, I can tell you it'll have a double bond, and it'll have 4 groups attached to it. So it'll have the double bond between the alpha and beta carbon there. And your choices are that the 2 methyl groups will be cis, or the 2 methyl groups will be trans in that final product. When you lose this hydrogen, the pair of electrons is going to come in, kick off the amine, and so the question is, are the 2 methyl groups going to be cis, or are the 2 methyl groups going to be trans?
Why are there 4 groups of
One of them is a hydrogen. There's 4 things attached to the double bond. A hydrogen, 2 methyls, and an ethyl. So my question is, what's the relationship between the 2 methyls going to be? And I'm going to give you 3 minutes to work on that. Because anybody who's willing to put up their card right away may want to reconsider that and think about writing out what the transition state's going to look like.
For the other products, so like it ends with the 3. Is there a plus charge also?
No?
Can you like write it out?
How do you write out what?
The other product.
Oh, the other product is going to have the H attached to the nitrogen with the 3 methyl groups. So there is going to be a plus charge on it. So for Hofmann elimination, what's going to be the final stereochemistry of the 2 methyl groups? Well, that's what you got to figure out.
What are you going to designate as the option? Is that A or 6B?
I will write that out when you get an answer. Two minutes from now, I will ask you. Your time is up. So let's vote. Your choices are the two methyl groups are going to be cis, or the two methyl groups are going to be trans. So you should have had one of those two in your okay. All right, let's see what we've got. We got 10. We have more than 16 people here, don't we? How many we got, Sarah? Are any of you counting me? Okay. All right, so 16 is close to one of those answers. It was 6 A's and 10 B's. So how are we going to answer that question?
If I recall correctly, the two leaving groups need to be in,
Two leaving groups?
right? You have a hydrogen that's going to be removed, and then you have the N+ group that's going to be removed, and the anti-brainer.
Stop there. So I need to and I'm going to put the 3 methyl groups in brackets. Okay, so I need to put the nitrogen plus and this beta hydrogen anti-periplanar. Alright, I gotta go into this mode then. And I don't like this mode. Okay, so I gotta put them anti-periplanar. So let's just use the existing structure here. And so I'm going to rotate groups, right? So let's rotate the nitrogen down to the methyl group. And then let's rotate the methyl group back into the hydrogen and rotate the hydrogen up where the ammonium was. So now I've got the ammonium on the position that's in the plane of the board. So over here, what do I have to do? I'm going to have to rotate that hydrogen up here. I'm going to have to rotate that ethyl group down here. And I'm going to have to rotate the methyl group back there. So now I've got this in an anti-periplanar geometry. And so now the hydrogen comes down, the nitrogen goes, and so I get the double bond. The two bolds are cis. The two dashed are cis. And so the methyl group should have been cis. The two methyl groups will be cis.
Can you also look at that based on like stability and like steric energy? Or not steric energy, steric convention?
No. No, I've got to put that hydrogen and that nitrogen group in the anti-periplanar geometry. That's the only way to look at it. Now, you could look at it as a Newman projection, right? You could say, oh, well, I'm going to be over here, and I'm going to be looking at it that way, so that the hydrogen and the methyl group and the ammonium group are now anti-periplanar. Let's see if I finish that off. The ethyl group is forwards. So this is me looking at the molecule to make this. This is me looking at the molecule to make the Newman. So then on the front side, the hydrogen is forward and the methyl group is in the back. And then over here, the methyl group is in the back. And then when I lose the hydrogen and the ammonium group, it flattens out. So that again, the two groups that were bold are cis, the two groups that were dashed are cis. Been a while since we've done this, but we have done it. So we have to go back and just remember how to manipulate the sawhorses. Now, what's going to happen with the cope? How are the methyl groups going to be oriented? Well, the transition state is going to be periplanar, but in the end, the two methyl groups should be trans. Because if it's the same molecule, one's going to be cis and one would be cis, and then the other one would be trans because they have to be opposite. If it's not the same molecule, who knows? And the only reason I say that is because on the exam, if I gave you the same molecule and said, here's the cope, here's the Hofmann, then you know that they have to be opposite if it comes from the same molecule. But if I gave you two different molecules, you got to do each one individually. So how would I do that one? Let me rewrite the molecule then, the original configuration. Only now my nitrogen will have gotten two methyl groups and it will be, well, it'll be hit the amine oxide with the hydrogen and the methyl group. So now what I have to do is now I have to put that in the U-shaped, and when I mean U, I mean the bonds that are in the plane of the screen, that I have to put it in the U-shape with the bold and dashed wedges. Now everything is eclipsing each other, right? This is the eclipsed conformation. So on the left-hand carbon, nothing changes. So what am I going to do to make the right-hand carbon, this nitrogen, go into the plane? Right now it's pointing towards you, so I'm going to have to take it back. And then what happens? The methyl group that's in the plane, as this one goes back, the methyl group comes slightly forward, and the hydrogen is still behind. So I'm going to make a half rotation, or like a 30-degree rotation. You don't like that? I'm going to rotate this back, rotate this one forward a little bit, and this one forward a little bit. And so when this one was in the plane, it comes forward out of the plane. You still don't like that? Well, if you don't like that, then let's put this into a Newman projection. See, that's why I don't like put it in this mode. 'Cause it just draws spray stuff. Alright, we agreed that this is the Newman projection for the sawhorse, for that sawhorse. Alright, so then here's my front carbon has the ethyl, the methyl, and the hydrogen. So again, I'm over here looking at this molecule to get this structure, and looking down is what gives me this. On the front carbon, the methyl group is in the plane. The nitrogen is in front, and the hydrogen is in the back. Okay, so there's the Newman projection. Yes, but since I'm getting looks, and those looks don't faze me. I've seen them before, but at least then I'm like, okay, let's try another approach. If you didn't see the fact that I'm going to rotate the nitrogen back, now what I'd like to do is I need to put this hydrogen and the nitrogen group eclipsing each other. So I'm going to rotate the nitrogen, the back carbon, I'm going to rotate this way. Okay, so my back carbon is now going to go into the eclipse mode. So there's my nitrogen, my 2 methyls, and my O minus. Then the methyl group on the back carbon goes there, and then the hydrogen on the back carbon goes there. And then front carbon, I'm going to have to move. I'm going to have to move the hydrogen up here, the ethyl group down here, and the methyl group there, in order to put that hydrogen there. So then the methyl group comes over here, and the ethyl group comes down there. So there's my front carbon and my back carbon, and now they're eclipsing. So this, hopefully, is that.
Power, I guess you could say, to move the positive rotation to go through, and it's almost basically two eclipse.
It's not that it has a power to it, it's that it has to. In order for the transition state to occur, and remember, I'm heating this, so I'm giving it thermal energy. But I need to put this into this. I need to put it in this periplanar conformation. That's the only way that the oxygen grabs the hydrogen and does that. It's got to go into that conformation. Over time, maybe, just because of the thermal energy in the system. But heating it'll make it go a lot faster. But I gotta put it in this conformation. So now this grabs that goes in, the pair of electrons goes to the nitrogen, and the hydrogen and the methyl, and the methyl and the ethyl. Let's be careful here. Not screw up the molecule. the methyl and the ethyl are attached to the same carbon, and then the methyl is cis to hydrogen, and the ethyl group is cis. So that would be the major problem. This, because I have to put the nitrogen. And why did I draw this one? Because I showed you that I was rotating this back to form that. And then over here, what I'm going to do is here, I would then rotate this hydrogen up here, ethyl group down here, methyl group there, to put it into the final conformation to have it react. Well, I could. So then I got to do this, right? I've got to rotate this hydrogen up here, but a little bit further to get it in front, and then rotate this down, but then a little bit further to put it in the plane, and then rotate this methyl group back and a little bit further so it's still back. So I've got to rotate that molecule into that one. One on the right twice. I can do that, but here's the thing. Full rotations here don't ever make this eclipsed. I've got to eventually go from staggered to eclipsed. So I have to make that little extra third twist in order to make that happen. So what I originally did was I just took this group that was forward and rotated it back. And then to make that, then everybody gave me, or a lot of people gave me looks. So then I'm like, okay, that didn't quite make sense. So now let's convert this into a Newman projection, and now let's go ahead, make that little rotation to make it eclipsed, and now let's line it up. So there's 5 ways to do this problem. Find one that will give you the correct answer all the time. Or find one that will not give you the correct answer all the time, and then reverse your answer at the end. Sarah.
So basically, like, you get to rotate
I'm going to rotate this. I'm going to rotate this entire carbon back 60 degrees. One carbon. If I rotate both carbons, I'm just endlessly rotating the molecule around and never making another conformation. So I've got to pick one carbon and rotate it 60 degrees to put it into this U shape. And this goes back, I mean, when's the last time we did this? It could have been last week, and it still would have been a long time ago. But the idea is that if you go back and you kind of remember back when we were doing this, we said, okay, here's my 2 possible sawhorses. And this one corresponds to eclipsed. And this one corresponds to, this one corresponds to staggered, and this one corresponds to eclipsed. So, this is Cope, and this is Hofmann. So, whatever staggered conformation I give you, or whatever sawhorse projection I give you, you've got to put that sawhorse into one of these 2 conformations so that either the hydrogen and the leaving group are anti-periplanar, which would be the case for Hofmann, or the hydrogen and the leaving group, the amine, are eclipsing for cope. This is the same as what we did back for E2. Cope is new. So when we get that molecule, we have to decide, what am I doing, Hofmann or am I doing cope? And so then I have to put it in one of those two conformations initially and then rotate around so that I can put my nitrogen with my O- near my hydrogen, or over here put the ammonium down there. I don't know that stability comes into play here. Because it's not about stability, it's about putting the molecule in the correct geometry. It may be that the Hofmann is the most stable product, but it doesn't have to be. It is. I mean, the Hofmann product is, because it's starting out in that geometry where if I put the beta hydrogen and the leaving group anti-periplanar, that's the product I get. For cope, it's the same thing. So we really can't judge stability. We're just kind of writing the final product. So you asked earlier, why would you do these two? Well, if I wanted to make, go back to that molecule, I want to make the two methyl groups cis, I need to use Hofmann. If I want to make the two methyl groups trans, I would need to use the cope. So I can plan out which reaction I want to use to make that product. And the reality is, I could use either one of them to make the least stable product. Maybe the one with the most steric hindrance between the two groups on the side. So for instance here, having the ethyl group would probably be better cis with hydrogen than having it with the methyl group. But if this is the product I want to make from this original molecule, I have no choice. I have to use cope to make that product. So it's really not about it's not about stability, it's just about getting the molecule in either periplanar or anti-periplanar geometries. So on the next exam, which is a ways away, but not that far. I know. Trust me, I know. I might give you this molecule and ask you to do it both ways, and the first thing I might say is write the major product. Then you go back and you go, oh, well, the major product is that. But then I might say write the other product, and the other product coming from the same molecule is going to be the E. If one's E, then the other's Z, or vice versa for Cope and Hofmann. So that's the difference in the stereochemistries. And it'll take some practice to do this. I will dig up some practice problems over the weekend, and also then they'll ask you to do this in the top hat problems. Right, so does that kind of make sense in terms of those two? It's been a while since we've done this, but we have to go back and play with the sawhorses. And like I said, you can convert it to a Newman if you can see that, if you can rotate it yourself, if you can just see it in your head. okay, of what works for you. But usually you have to write something down. Okay, so you got to do that. So the amine chapter of Top Hat, all that's what's left is stuff we've done. Diazonium salts. Been there, done that. So now you can do some Top Hat problems on diazonium salts. And the only other thing I think that's at the end of the semester, or at the end of this chapter, is I want to convert an amine to a amide How do I do that? What? We did do that in lab. So if you can remember what we used in lab, well, see, that's the problem. We did in lab, but we forget what the reagent is. And we're going to actually learn about that reagent here over the next couple of weeks. We use the acetic anhydride. But how else can you do it? Use an acid. Which we'll learn about too. You could do it with a carboxylic acid, but it won't work right off the bat. We need to use a carboxylic acid. So diazoniums and making amides from acid chlorides. That's the end of the amines chapter. So technically then, since we finished that chapter today, the problems would be due to lecture periods from now, which is Monday, Wednesday, would be due Wednesday, but we'll make them due the Wednesday before the exam. And the other problems, the target date is Monday for those. Though if you notice, I have not gone and written the scores down for the last chapter, so if you're behind on those, you could have the weekend to get caught up. But sucks to do that because the whole idea was to do those before the last exam. So remember, next week we have class on Monday, Wednesday. It's a normal week. Days are all the same. Then the week we come back, we have class on Tuesday, Wednesday, and Friday. Well, and so I said this morning, does everybody know why we have these phantom days when they become other days? Why? No, not really. It's basically, so the answer is no, we've never been told the big secret at John Carroll, which is why do we have Monday classes on Tuesday when nobody else in any other university does it this way? The reason we do that is sort of for lab, but so that we have an equal number of Monday, Tuesday, Wednesday, Thursdays, and Fridays. Because if you have a class one day a week and you miss a day, you miss a week of classes. And so that's how we do it. That's why. If you look, we're missing Monday, Tuesday becomes Monday. So that's why we do that. All right, if you have questions, the only thing due on Monday will be the top hat problem. I'll take your homework problems for today. The only thing that's due on Monday are the top hat problems, and then I'll probably give you some more stuff then.